Bismillahirrahmanirrahim. I'm sorry, we have some problem in our internet. So we got disconnected. I'll again start from corrosivity. If possible, there is a strong incentive to use a component that is already in the process, such as reactant feed stream as the solvent. This may avoid additional material handling, environmental and corrosion penalties later in the process. We usually, what we do, we basically try to use the reactant feed stream as the solvent, which is which is reacting with the feed stream, and this will later it will be basically it will aid in avoiding the additional material handling and the environmental and corrosion penalties. Toxicity is an important factor while you are doing the extraction process. Why? The advantages of non-toxic solvents are self-evident in considering inherent process safety and capital costs. Some solvents are now appear on the environmental red list and should be avoided. Because if your process is for human consumption, then also you need to have a solvent which has less toxicity, and also for the environment it should always be considered to get a substance which solvent which has low toxicity. And there after this global warming and after all these things, so we get some there are some compounds which are solvents which are in the environmental red list and which should not be used and should be avoided, because the extraction process may only be a small part in overall process, and solvent losses should not greatly affect process economics. It should be, before doing that extraction, because a large number of solvent is used. So before using that solvent, you must keep in your mind the cost of the whole of the process, because extraction is usually not the only process you are doing. You have to, evaporate it, or you have to then make other things as well after the extraction process. This is the only one of the step in making a pharmaceutical preparation. So the cost should be keep in mind. Commonly used solvents, these are ethyl acetate, diethyl ether, dichloromethane, and chloroform. They dissolve in about 10% in water, while water also dissolves in organic solvents like ethyl acetate, diethyl ether, dichloromethane, and chloroform. How much water is dissolved in it? It is written how much ether in ethyl acetate, 8.1% water. If you are taking, then 10% of water dissolved in it, while there should be some points which should be considered while you're doing the liquid extraction. The solvent should be able to dissolve at least one component to a large extent than the rest of the component in the mixture. What the solvent you are using or you are taking, it should be able to dissolve at least one component, so you will get a good separation. If it will carry other components as well, then your separation, you will again have to do a different separation. You'll again need a separation to get your desired component. So the desirable thing is that your solvent should be able to dissolve at least one component. The second thing is the reaction taking place should be stable and irreversible. Whatever the reaction is taking place, it should be stable and it should not be reversible, because reversible reaction can bring back the dissolved components in the previous form and the extraction will not be completed successfully. If it is not reversible, if it's not irreversible, if it's reversible, then of course your dissolved components will come back into the original form. The compounds formed after the reaction should be easily separated from the extracted compound so that it can be reused. course, the compound formed after the reaction should be easily separated from the extracted compound so that it can be reused. The density of the compound should be different from the required component to help the separation readily. Of course, it should be the difference in densities should be keep in mind. It should be inexpensive and cost effective. And, I've explained to you just right now. The solvent should not be toxic or corrosive as it can harm the extraction instrument. And other factors important during solvent extractions are viscosity, boiling point, and flammability. These things should be kept in mind. Okay, now I'll explain you distribution coefficient a little to have a more clear idea of the basics of the liquid-liquid extraction. When a solution is placed in a separatory funnel and shake with an immiscible solvent, solutes often dissolve in part into both layers. The components are set to between the two layers or distribute themselves between the two layers. When you shake two immiscible liquids in a separating funnel, they form two layers, and your component, what it is said that your component is distributed between these two layers. It is distributed. When equilibrium has established, the ratio of concentration of solute in each layer is constant for each system, and this can be separated by a value of K. So what is K? K is the partition coefficient or distribution coefficient, which can be defined as Kd is equal to molarity in organic phase to the molarity in aqueous phase. When a compound is placed in contact with two immiscible liquid, then the compound itself gets distributed in these two liquids. Of course, this is the basis of the distribution of the partition coefficient. This is an equilibrium process, means dissolution, and it is also known as dissolution equilibrium, governed by temperature of the system. Of course, in a certain temperature, it is, it gets on a fixed temperature. Basically it gets this equilibrium process, and if you increase or decrease the temperature, then it will the equilibrium process will be affected. Suppose compound A is to be extracted from aqueous solution into organic liquid, then for compound A, dissolution equilibrium can be represented by the equation. This equation is basically for the equilibrium state. Under dissolution equilibrium, concentration of compound A in aqueous phase and in organic phase is definite. That is, Kd is equal to concentration in organic phase divided by concentration in aqueous phase. Now, the large-scale extraction or the large-scale extraction processes. Usually, the large-scale extraction processes are basically somewhat they are doing only one extraction process, but certain times there are two or three types of processes, or there are two sophisticated processes which are interconnected. Like in this, you can see that it has the extraction tank where the extraction is taking place, and after that there is a continuous extraction phase is also connected. So you get your whatever you have incorporated, you are getting it back. This is a continuous phase, and then a HPLC column is also attached, which basically is purifying to its finest form, or to the component, each component form. So this the large scale extraction processes are usually like this. They are usually big plants. From there, or industrial plant. I mean, I'm not saying the plant in herbal plant. I'm saying the industrial plant. They are usually the big type of plants in which 2 or 3 processes are mixed together to get a final component. That's why, I was saying that you should select your solvents very carefully. So because this is not a small process, it is going to be a continuous process, and you are going to use, so it should be cost effective as well, because you don't have to perform only one of the extraction process, but you are doing other things as well, which are more complicated and they need more sophistication and they are more expensive. So you need to, select each of your step very carefully, and especially about the cost. Large scale extraction procedure. Large scale operation demands modification of many extraction processes. The basic extraction process is same, but you have to modify your extraction processes. Why? Because for example, it's given that in case of jar or vessel containing a small amount of solvent, occasional shaking is no problem. But for industrial batch where a large amount of solvent and the vessels having the huge weight, diameter and height, there will be considerable difficulty in shaking the vessel. Of course, when you have a separating panel, you can, hold it in your hands and you can shake it with your hands. So it's not that difficult. Even if you are dealing with 5 to 1,000 ml solvent, even then there is no big problem. But in industries, the batches are, really big batches. So there are gallons of liquid. So for that, shaking is not that easy. There are alternative methods of agitation that are just as effective, but much simpler to put into practice. In addition, economics become increasingly important, and one of the most important objectives is to improve the efficiency of extraction so that less solvent is needed and evaporation requirements for concentrated products are reduced. When you're, doing that in a lab, if you're using only 500 to 1,000 ml, so there are not much of, even then the process is expensive, but it's not, that will affect you. But if you are using gallons of solvents, and of course your process will get cost effective. So you need to, keep them under control. So you need your solvents to be reused again and again, and that's how you will make it cost efficient. By reducing the cost of evaporation, it has the further advantage of minimizing the heat damage to thermolabile consumption. And also you need, you don't want your evaporation procedure to be to be done in very high temperature. So you also need your evaporation procedure to be considered, because thermolabile constituents will get damaged if you apply high heat. So all these things need to be considered while doing the large scale extraction procedure. What we do if you modify large scale maceration process, one of the example is the circulatory extraction. The efficiency of extraction and maceration process can be improved by arranging for the solvent to be continually circulated through the drug. Because in maceration, what you do, you get your you take your plant or whatever thing you want from extraction from, and you soak it in your solvent. Okay, but then you take out that solvent, and your solvent will have that desired component, and then you don't use it again and again. But for a large scale, you want it to be continuously circulated through your drug, because certain times you can get your component in the first extraction, but it's not necessary. You maybe some of your very expensive and very desirable component is still in your plant material or material which you're extracting from. So you need to have a continual circulation of that solvent to get that desired component in its maximum level. Solvent is pumped from the bottom of the vessel to the inlet, where it is distributed through spray nozzles over the surface of the drug. How you do it? You basically pump the solvent from the nozzle or into the vessel. The movement of the solvent reduces boundary layers, and the uniform distribution minimizes local concentration in a shorter time. This will help in a uniform distribution of the solvent. And this is how a big macerator look like, or circulatory extractor looks like. You know, you continuously spraying your solvent which you are collecting from the which is passing through your plant material, and you're collecting at the bottom, and you're again pumping the your solvent from to the upper portion of the plant of the whole equipment, and you are spraying it again. Multiple stage extraction, like the normal maceration process, however, extraction is incomplete since mass transfer will cease when equilibrium is set up. This process can be overcome by using a multi-stage process. If the equilibrium is achieved in one or two type of extraction, one or two time, you know, you're spraying your material, your solvent, and if that solvent, you know, is in the equilibrium state, then of course your component will not, you know, get extraction. The extraction will not happen, because your solvent is at the equilibrium state of the menstruum or the plant materials. So to overcome that problem, there is a method known as multi-stage process. The equipment needed for this method is a vessel for the drug, together with a circulatory pump and spray distributor, and a number of tanks to receive the extracted solvent. The extractor and tanks are connected with piping and wells. I'll show you the figure, so that any of the tank may be connected to the extractor for the transfer of solution. Examination of these procedures showed that each batch of drug is treated several times with solvent, and that once a cycle is in process, the receiver contains solution with the strongest in receiver 1 and the weakest in receiver 3. This is how it is done. Then what are the advantages? The drug is extracted as many times as there are receivers. In this case, the 3. If more extraction stages are required, it is only necessary to have more receivers. The last treatment of the drug before it is discharged is with fresh solvent, giving maximum extraction. The last treatment of the drug is with the freshest solvent. The solution is in the contact with the fresh drug before removal for evaporation, giving the highest possible concentration. What is the procedure basically? Procedure is that you fill the extractor with drug, add solvent and circulate. Run off to first, it will go to the receiver 1. Refill extractor with solvent and circulate and run off to receiver 2. Refill extractor once again with the solvent and circulate and run off to receiver 3. Remove drug from the extractor and recharge. What you do, you remove your drug and you again, you know, do the same procedure which you have done. If you have crushed it, you will crush it again. Return it from return solution from 1 to extractor. Remove for you will do what you will do. You will put your material in that container, and from 1 you will return remove from 1 to the extractor, remove for a web, then you from after that you will remove from the extractor 1 and you will give it to the you will send it to evaporation. Return solution from 2 to extractor and circulate and run off to, then you will the one will be empty, and because you have given it for evaporation, so the 2 will come in 1. Return solution from 3 to extractor and circulate, run off to the receiver. It will go into the receiver 2, and then add fresh solvent to the extractor and circulate to run off to the 3. Now the remove drug from the extractor and recharge, and that's how you repeat the cycle again and again. Okay. There is one more, there are many large scale extraction procedures, but I'm only I'm only discussing few. There's one more which is known as extraction battery. In the normal percolation, this is a basically enhanced or modified percolation method. Okay. In the normal percolation process, the percolate is not of maximum concentration and as such very dilute. The ideal situation would be to have maximum concentration. Continuous extraction device of this type are used where large amounts of single material are handled. It can be achieved by treating it as a stage-wise process. In this process, a series of vessels are used and extraction is semi-continuous. Equipment, it is described as an extraction battery and consists of a number of vessels with interconnecting pipework. Vessels are so arranged that solvents can be added to and the product taken from any vessel. These vessels can therefore be made into a series with any of the vessels as the first of the series. The use of extraction battery is illustrated in the figure I'm going to show you. The simplest arrangement of 3 vessels is shown. This is how battery looks like. It is composed of usually of 3 tanks, and as I have illustrated, as the author is illustrated in this picture, that they are different vessels, but the introducing the solvent and taking out is different at different stages. There are 5 to 6 stages where the removal, the addition and removal of the solvent is different. That's how you know you modify your process. Okay, that's all for today. Thank you very much.